and our final talk for this session will be on handling the selection monad.
All right. Hello, everyone. I'm Ningning here from the University of Toronto and Google DeepMind, and this is joint work with my colleague Abadi and Plotkin at Google DeepMind. I will start the talk with a small program as a motivation. So consider doing binary search that searches an ordered array A for a value x. So the program here takes a value x and the array to search for, as well as the range of the array we will be doing the searching in this case from L to R. And at each step of this function, we are going to pick an index m and compare the element at am with x. If they are equivalent, great, we are done. Or otherwise, if am is smaller than x, then we are going to recursively doing the search for the elements from m plus 1 to R, or otherwise we are going to recursively do the search from for the elements from L to m minus 1. And now the question is, at each step of the function, which m should you choose? Well, of course, we want better m's because ideally we want as few recursions as possible. And the way we are going to do it is we are going to say that each recursive call is associated with a cost of 1. So you have to pay to recurse. And also, we know that whenever we are choosing this index m, we are going to choose from the range between L and R. And we can also provide some context information, like in this case, the value of x, as well as both values at the ends of the array. So now a clever implementation can take into account, for example, the distribution of the data, as well as the records of past decisions we have made in order to decide better how to select this m. And this example is actually chosen from the Smart Choices APIs developed at Google, which allows programmers to provide choices, context, and feedback to the underlying server, which will perform training and deploy policies for this kind of decision-making problems. In this work, however, we study decision-making abstractions from a programming language perspective. To summarize our ideas in a single slide, in this work, we combine algebraic effect handlers with a form of continuation that we call loss continuations, which are computational ideas inspired by the selection monad. And we can call the resulting handlers smart handlers because they allow programmers to provide user-defined optimization strategies for decision-making operations, just like the binary search example we have seen in the previous slide. So in the rest of this talk, I will provide some background on algebraic effect handlers before I discuss how they can be combined with loss continuations. To explain the key idea of algebraic effect handlers, we consider an example handler for exceptions. So here, I have an effect for exception, which has a single operation raise that takes some exception information and returns a unit. And with this effective signature, we can use this raise operation inside the program. For example, here, we let y be bound to the result of raising e, and then we use this y in this function f. And the semantics of operations is actually given by handlers. So in this case, this handler is going to handle this operation raise. So it's going to receive the argument to this raise operation, and it says that I'm going to do some g using this x. And we can handle this program using this handler. And now when this raise operation is performed, the control of this program is going to be transferred to this handler. And in this case, the handler says that I'm going to evaluate this g with this x substituted by the argument to the operation, in this case, e. And this program is a simplified program, but it already demonstrates the modularity of algebraic effect handlers, which separate the syntax of effective operations from their semantics that are defined by handlers. And in this case, the exception handler aborts the original computation. And one important feature of effect handlers is that it has available the original computation where the operation is performed. So specifically, here we have the same effect and program as before, but when the operation raise is performed, we will also create a continuation that when called will actually resume the original computation. And in this case, the handler is also updated, so it receives not only the argument to the operation, but also a continuation k that's going to resume the original computation when this k is called with some input. And in this case, the handler says, well, I'm going to see whether this exception is a bad exception. If it is, then I'm going to abort the original computation, and instead I'm going to run gx. But otherwise, let's resume the original computation with the value 20. And now our original program will run like this. Well, when this raise operation is performed, the control again is transferred to this handler, and this handler is going to see whether the exception is bad or not. And in this case, we have allocated this continuation k that is bound to where the operation is performed, from where the operation is performed to where this handler is used to handle this operation. And in this case, we also reinstall the original handler so that you can have many exceptions in the rest of your program. And let's assume in this case, the exception is fine. It's an OK exception. So we are going to resume the original computation with 20. And you can see in this case, y is bound to 20. And ultimately, we are going to evaluate f20. And the continuation and the computation can continue. And more interestingly, with effect handlers, because this continuation is available as an argument, the handler can also resume the original computation multiple times. So in this case, I have updated, again, the definition of the handler. So when this exception is a good exception, we are going to resume the original computation twice, once with 20 and again with 40, and then maybe we have a way to choose the better result of these two rounds. So this is called a multi-shot handler. So now the original computation will run, and again, let's assume this exception is a good exception. So we are going to resume the original computation with 20 and 40, and ultimately we are going to evaluate f twice with 20 and 40, and their results are going to be compared according to some best function, and the final results will be returned afterwards. So having seen these examples, we can now define the formal semantics of effect handlers. So here is an example handler language. It's very similar to the core calculi used in most effect handler languages like Coca, Lynx, and other languages. And this is also extremely simplified, but the calculus in our paper supports more advanced types like sum types, product types, lists, natural numbers, floats, etc. So in this case, in the definition of type, we have really just the base type and the tuples and the functions. But the functions that goes from type A to B, the function also needs to keep track of the effect that will be performed when this function is called. And this effect epsilon, it can be either empty or it is some effect epsilon extended with an effect label L. And we have seen the signature of an operation like raise. So it's going to take some argument of type out and then give us back some argument of type in. So in the case of raise, we have seen that raise takes the type of the exception message and gives us a unit. And because this is a simplified language, so we really have just the two forms of expressions. You can either perform an operation, or this operation is going to be handled by a handler. So we can call this op by providing this argument m, or we can evaluate this computation n under this handler h. And in this case, we also support parameterized handlers, which are handlers that can carry a local parameter to it, which is very useful when you would like to implement stateful handlers that can have local states. And the handler is just a list of operation clauses, right? It handles all those operations listed here, and each operation receives the parameter to the handler, the argument to the operation, as well as a continuation k. And this continuation is to receive a potentially updated handler parameter, as well as the result of this operation, and is going to evaluate, in this case, the computation m. And a handler can handle many operations within it, and it also has a return clause that will be applied when the computation returned from the handler without performing operations. So we will not be giving the typing rules for this whole language, but here is the typing rule for handlers. So basically, a handler will need to keep track of the type of its parameter, as well as the computation being handled and the effects that computation can perform, and it gives you back the computation after after it being handled, and also the resulting effect. So you can see L here is gone because we assume the handler is going to handle some specific effect label L. So that's about effect handlers. Now the question is, where are loss continuations, and where do they come into play? Intuitively, we can consider, like, let's say there is an ordinary computation P with type A. So if you run this computation, it's going to give you back a value of type A. Now, a loss-oriented computation is a computation P that receives a selection function from A to real and then gives you back a real. So you can consider this real as that cost number we have seen before, or the loss that is associated to every choice of A. So this P says, if you can give me a selection function that tells me what kind of loss is associated to each choice of A, I'm going to give you back an A according to the selection function. So maybe this P will say, I'm going to return the A that maximizes the loss, or I'm going to return A that minimizes the loss, or it has some its own criteria for selecting this element A. And because we have this element A available and we have the selection function, so we can also return the tuple that has both the loss value as well as the element A. And if we look at the type signature of this loss-oriented computation, it looks very similar to what people call the selection monad in the literature. So the selection monad of X is basically something of this type. It also takes a function from X to R, where R is the real number, and it gives back an X. So if we generalize the type a little bit, we can also say the selection monad has type from X to Y to X. So then people who are familiar with continuation monad may notice the similarity and the differences between continuation monad and selection monad, where continuation monad goes from X to Y, and the selection monad goes from X to Y to X. And similarly, we can combine the selection monad with the loss monad and then return both tuples. And with that, we can now start incorporating selection monad into effect handlers. And the way we are going to do it is that we are going to add in one language primitive, and then we are also going to update the definition of the handler. So specifically, we have the same definition of types and effect signatures as before, but now we have one additional language construct that's called loss. So we can call this loss with a term M. So that is telling that the program that I'm currently incurring a loss of term M. And now the handler is also updated. So in addition to the handler parameter and the argument to the operation and the ordinary delimited continuation that we have seen before, it receives an additional continuation, which is a form of loss continuation that we call the choice continuation. So it's similar to the continuation that we've seen before in the sense that it receives the output of the operation. But different from the continuation that returns something of type B, this choice continuation returns a loss value, which is basically the cost or the loss value associated with each choice of the operation output. Now this handler can make use of this loss continuation, and this allows programmers to write handlers that handle operations according to this loss information and maybe resume the original computation with a particular selection of the operation result. So let's see some examples to demonstrate how things work. As a very simple example, we can look at a minimizer handler. So in this case, here the program password tries to choose the password from a list of candidates. So it calls this effector operation pick, and it provides a list of candidates. And whatever candidate is chosen, this program says there is specific loss associated with your choice of the password. Because maybe I want the password to be as long as possible. So there is this loss of the negative of the length of the password. And maybe also I want as many distinct elements in the password as possible. And after that, I'm going to return the passport that you have actually chosen. So this program is not responsible for choosing the ultimate password, but it knows that whatever password you choose, there is going to be associated loss. And now you can write a handler that actually does this password choosing, and this handler determines the choice using this loss continuation. And in this case, it's a minimizer handler, so it says, because I have a loss continuation available, I'm going to call some function minwidth that's going to select from the list of the candidates the element that minimizes the loss. And after I'm done with the decision, I know that I have chosen P as a password, and I can resume the original computation with the password I have chosen. So in this case, we are going to probably return AABB or ABC because they are both longer and have more numbers of distinct elements. And this program gives an example of what we can do with the loss continuation. And since we have this loss continuation available, we can also do more advanced things with it. For example, we can do linear regression. So this is an example that corresponds to one iteration of the training program for linear regression. And at each iteration, we are going to make a choice of the weight and bias that is used in this linear function. And we are receiving input data and then the expected output data. And at each iteration, we are going to apply this linear function to predict this y prime. But of course, this y prime can be different from the actual y we want. So there is some loss that occurs because of the difference between these two values. And afterwards, we are going to return the updated weight and bias. And now the handler can determine the choice of the new weight and the bias using automatic differentiation. So in this case, the handler will apply the automatic differentiation to this loss continuation and gets the gradients of the weight and the bias, and then do one step of gradient descent so that it can update the weight and the bias, and then it can continue the original computation with updated weight and bias. So I hope this gives you an intuition of how loss continuations are combined into effect handlers and how we can make use of them to make decisions by defining optimization strategies as handlers. So I probably won't have time to go through the formal development of the calculus. We have the operational semantics in the paper, as well as lots of the operational semantics rules. And we have meta theory developed. So we have proved our operational semantics preserves type, is deterministic, progresses, and also under some assumption that effect handlers are well-founded, we proved that our calculus is terminating. And there are more things that you can find in the paper. We also have fully developed denotational semantics that is proven to be sound, and we proved adequacy result that the denotational semantics coincides with operational semantics. And we have implemented our calculus as a Haskell library and provided more examples in the paper, including two-player games, hyperparameter tuning, and Nash equilibrium. With that, I'm happy to take questions.
Questions for the speaker? One up here in the front.
When you work with your selection monad, did it occur to you whether you should have titled your paper and oriented your work and called it handling the continuation monad instead of handling the selection monad? In other words, if you had just tackled the continuation monad, what would have been different and what would have stayed the same?
So it's a question that if we change the selection monad to the continuation monad, then what would happen? So that's a very interesting question. So with continuation monad, what you care is about the result of the final program. But with the selection monad, what you care is the input to the continuation. And this is, I think, the key for lots of decision-making process, because you don't care about the final value, but you care about the thing that, the choice that you have made in this process. So for example, if you take linear regression as an example, right? You don't really care about the final loss that is produced, but you care the weight and the bias that is produced in the end. So this is the part about the selection monad. So if you instead use continuation monad, I cannot imagine what the semantics will look like, but it's very likely that you will lose the information about the thing that you actually care about, which is the selection of the weight and bias in this case.
Take that offline since we're just about out of time, and let's do one brief question here if you have a brief question.
Yeah, sure. So on the same slide, the loss continuation L, does that also come from continuing with computation where you left off? Is that how that works?
Yes, so the choice continuation ultimately is a combination of the delimited continuation and the loss continuation in the context. So basically, it takes the result of the program and also applies it to the current loss continuation that will actually calculate the loss of the whole program.
Cool.
Great, and with that, we are over time, so let's thank the speaker again.
Thank you.